All right, so Nick gave a quick introduction, which I appreciate. So if you've been to my presentations at MongoDB World, you realize I tend to speak about things I'm passionate about. And one of the things that really irks me is a lot when people make technology decisions based upon misconceptions or bad information. And often one of the things that happens when I go around the country, and like Nick said, I work with some of MongoDB's largest, more strategic customers, is I'll find out, hey, we went with some other database other than MongoDB because we have this ActiveActive requirement. And really what I want to talk about today is when we talk about ActiveActive applications, what does it mean? And how does MongoDB fit, and in what situations can you use MongoDB for ActiveActive applications? So when we talk about ActiveActive, what people typically mean is we want to deploy our application across multiple data centers or regions, and in each region we want to be processing customer requests. So in this case, we've got our application distributed across 2 regions, and we have app servers in both regions. Both app servers will be actively processing customer requests. They will write data to local copies of the database, and magically data is replicated across those regions. And there's also typically some notion of if we lose a region, it'll automatically fail over and all that type of thing. The pushback you can sometimes get with MongoDB is that, hey, MongoDB has this architecture where the basic unit is a replica set where there is a single primary. And that means if we deploy our application across multiple data centers and want to do ActiveActive, there is going to be at least one set of application servers that when they want to do writes have to write across the public internet or a wide area network, and performance is going to suffer in that scenario. And that argument can be used to eliminate MongoDB for a whole class of applications. And what I really want to talk about today, is this true, and under what situations could it possibly be true? So to me, whenever you're trying to determine is a technology a good fit for a particular scenario, it's a good idea to make a list of all of the requirements. So let's kind of step back and understand what are the requirements if we're going to build an ActiveActive application. So first, I'm just going to assume that there's a set of database requirements, like we need to store data, read queries, and all that stuff that we're just going to ignore for now. But just from an architectural perspective, I think there's 4 categories of requirements. One is you want high performance, typically measured in latency. And what that means is you want to be able to read and write from a local copy of the database so that you get millisecond performance. Once you start reading across long distances, you're starting to get queries in the second range, which most of the time are not satisfactory for applications. The second is you want consistency. And typically, they're requirements around things like when you issue a read, you want to see the results of all previous writes. When you read in one region, you should get the same answer as you get in another region, things like that. For availability, you want this whole infrastructure to just continue to work when pieces fail. You lose a node, a data center, the network split, whatever, to just work. And then finally, with durability, when you issue a write, you expect it to be immediately replicated across all the different nodes so that everything is fault tolerant. So let's drill into each of those requirements. I think they're easier to understand pictorially. So first, with the performance around latency, really what we want is we want to be able to read from local copies of the database. Similarly, we want to be able to write to local copies of the database. And we don't want to do this, right? You don't ever want to be in a scenario where you need to read and write across data center boundaries or region boundaries. For consistency, right, there's all sorts of things that could potentially go wrong with consistency when you have a distributed database, right? So if we issue a write and we're updating the same record in 2 different regions, so I have some fictitious document, or it could be a shopping cart or somebody's bank account or whatever, we update it in 2 different regions, then you're going to get some strange behavior sometimes. Like you might issue a read and not see the result of the previous write, depending upon which node you read from and how fast the replication works. Similarly, you might issue a read in different regions and get different results just because of the fact that you updated the same record in 2 different regions. And then you also have this replication challenge where potentially if we've updated the same record in two different regions around the same time and we go to do our replication, now we've got each side of the database suggesting a different value for this document or record, and typically one of those is going to win. Most databases that allow this type of thing use some sort of conflict resolution strategy, like the most recent write wins, the one that made the most changes wins. So you're going to lose some information because one of the writes is going to get preferred over another. And then similarly for availability, we want to make this whole infrastructure continue to work if we lose a node, if we lose a region, or there's a network split. That's pretty straightforward. And then finally, when we're designing this application, we want the replication to work really fast so we don't lose data. So if we issue a write, we hopefully that write gets replicated to other nodes in our distributed database before that failure occurs, so we don't lose any information on essentially a node or data center loss, right? So these are kind of all of the requirements. And I don't know if any of you guys realize this, but the Rolling Stones, they were before their time. They really knew a lot about distributed databases, and that's what this song is about. And really, you can't get all of those things, right? So you have to pick one. You have to pick those 4 requirements. You have to pick the ones that are most important to you, and design or pick a technology or configure your database to satisfy those requirements, realizing you're going to sacrifice some of the others. So if you're out there picking a database technology, you have to, and it's going to be a distributed solution, you have to kind of look at that database technology and say, which things of those 4 properties are it going to give me, and which ones am I going to have to sacrifice? The real powerful thing about MongoDB, which I'm going to talk about next, is based upon configuration options that architects and developers can use, you can configure MongoDB across a wide spectrum of consistency, availability, durability, and performance. So what I'm going to do for the remainder of this talk is I am going to first jump into talking about replica sets and talk about how you can configure MongoDB for different types of consistency, availability, durability, and performance. Once we have those foundations, we'll then talk about how you can lay out replica sets to achieve ActiveActive, given the fact that we can tune these different parameters for availability, durability, consistency, and performance. So let's kind of do our quick deep dive into MongoDB replica sets. And we're going to look at, I'm going to kind of quickly walk you through the set of features that MongoDB has for tuning these different parameters. And what my purpose today is just to give you an intuitive feel for each one of these. I mean, last year at MongoDB World, there were sessions on read concern that were 45 minutes. So I'm only going to give you a taste of what's possible, but you can go look at the documentation or talk to me after, and we can kind of drill into each one of these capabilities. So just as a refresher, probably everybody in this room knows what a replica set is, but just to make sure everybody's clear. In MongoDB, the basic unit of a cluster is called a replica set. There is a primary and some number of secondaries. The writes go to the primary. They're replicated asynchronously to the secondaries. And built into the replica set is this notion of automatic failover. So if you lose a node, like the primary, the remaining nodes in the replica set will hold an election. And in about 2 seconds or so, they'll elect a new primary, and processing will continue in the replica set. So that's the basics. But we can tune the behavior of a replica set with lots of these different parameters I talked about. So let's talk about how we can tune replica sets for read availability and write availability. And there's 2 main features for doing that in MongoDB. There's read preferences and retriable rights. So let's kind of drill into those. So in MongoDB, if you just install MongoDB or you deploy a cluster in Atlas and you don't change anything, every time you issue a read query, there's an optional argument called a read preference, and the default is primary. And what that means is when you issue a read, all of the reads are going to go to the primary of the replica set. And the reason why we do that is that gives you the most consistent view of the data. Essentially, we're guaranteeing that all the reads will see the results of previous writes. The problem is that if you try to read and you're issuing a read preference of primary, then you can't. If there's no primary and you have a read preference as primary, you can't read. So there is going to be a loss of read availability in this scenario. But you have the option of other read preferences that you can choose. One example is read preference of primary preferred. And what primary preferred says is I want you to read from the primary, so I get this strongly consistent view of the data. But if there isn't a primary available, then you can read from a secondary. And what that does is that trades off a little bit of consistency, because every once in a while you're going to read from a secondary, and that secondary may have a less current view of data than the primary. But you're giving your replica set a higher level of read availability. So you can consciously make that trade-off. There are other read preferences like secondary preferred and nearest and things, which I don't have time to go through, but there's lots of different configuration options that you can use to trade off consistency and availability by using read preference. So similarly with writes, if you're trying to write to a replica set and a failover is occurring and there's no primary, writes, you can't write. In MongoDB, in order to ensure consistency, we only allow you to read or only allow you to write to the primary. And there's nothing you can do about that because consistency in MongoDB is kind of the utmost importance. If you think about those trade-offs, MongoDB is much more skewed to the consistent end of the spectrum than some other solutions. But we do have an option called retriable rights, which basically means that if you issue a write in your application and a failover occurs, once the replica set failover has completed, then MongoDB will retry that write. So you can be assured that when you issue a write, without doing a lot of complex error handling in your code, that that write will be written to the database whether a failover occurred or not. So that's kind of one way to essentially increase, at least in a small way, the write availability of your MongoDB cluster. So let's talk about consistency. So like we talked about already with read preferences, by reading from primaries and secondaries, you can trade off consistency. And we also have other options around read concern that allow you to trade off consistency as well. So let's talk about that. So the first thing we talked about, if you read from the primary, you get strongly consistent. If you read from the secondaries, your secondaries, I want to say eventually consistent, but it's a little bit better than eventually consistent because in MongoDB, we guarantee that the secondaries reflect a past state of the primary. So the secondary may look like the primary did 300 milliseconds ago. But so when you read from the secondary, you get availability because you have more nodes, but you essentially have sacrificing a bit of consistency. But there's some challenges when you start doing reads and failovers with consistency. So let's talk about some of those. So let's think we have a situation now where we've got a replica set, this document, the current state of this document is x is 100. In our application, we're going to increment it and make x 101. So we issue a write to the primary, and then the primary writes that value to disk, and then some application reads that value, and everything seems great. And then what happens is the primary fails. So now we're in a situation where our main application or one of our app servers has written this value of x is 101. Some other app servers read it as x equals 101. The primary fails, and then a new primary takes over, and all of a sudden we're in this scenario where the new primary says x is 100, and you get this really strange behavior in your application where at one moment you showed the user this value of x is 101, and then all of a sudden the next second later, because a failover occurred, you showed the value to the user as x is 100. Think about if this is somebody's shopping cart or bank account or something. They would be really frustrated to see this application. It would look like a bug to them. So there's that one challenge that you could potentially run into. But fortunately with MongoDB, we give you this ability to trade off consistency for performance and durability and things like that. So what we could do when we issue a read to MongoDB is issue a read with a read concern majority. So if we're in this scenario where the primary has the new value, but the value has not been replicated to the other nodes in the replica set, what we can do is we can issue the read with the read concern majority, and then the primary there will return the value that it knows has been replicated to a majority of the nodes in the replica set. So it's not going to return the current value for this document, but it's going to return the value that it knows will never be rolled back because a majority of the nodes in the replica set have that value. So essentially what you're going to do here is you're going to trade off a little bit of recency of information in your application, but with the assurance that it's going to be a much more consistent view of the data. The second thing that you can run into if you read from secondaries around consistency is you can get into this strange behavior where an application can write a value, like again, we're updating our value from a 101 from 100, and then we read from a secondary, because maybe we're trying to leverage the extra hardware we have, so we're going to do all our writes to the primary and scale our reads by reading to the secondary. But you can get this really strange behavior again where you just write the value to the primary and then read the same thing from the secondary, but it hasn't been replicated yet. And now again, you get this strange behavior where it looks like the application has this bug because I just told it was one value and I read it and I get a different value. So we also have the option in Mongo when you issue a read from a secondary to read it with causal consistency. And when you do that, what happens is if I update the document and then read from a secondary, it will wait. So that the secondary isn't going to return my value until it is sure that all the changes that I've made have been replicated. So in that way, again, I'm going to trade off some latency, but I'm going to get a much more consistent view of the data. And keep in mind that these nodes, and what we're going to get to eventually, is these nodes are going to be distributed across multiple data centers. So all of this will be significantly more impactful as these clusters are deployed across multiple regions. And then the last thing we can do in terms of trading off these parameters in MongoDB is tune durability via a write concern. And what that means with a write concern is essentially the number of nodes that have saved the change to disk before we acknowledge the write back to the application. So the default in MongoDB, if you just don't do anything when you issue a write, is that you will get an acknowledgement back from MongoDB when the primary has written the data to disk. But it doesn't tell you anything about whether the secondaries have saved that data. So if a failure occurs, so if we write this value and a failure occurs, the new primary that takes over will not have our change, right? So you can get this perception from the user of the application that some data essentially disappeared because we wrote the data, the database acknowledged it, hey, I got it, it's done, and then a failure occurred and the new node that took over doesn't have that value. So the way you can get around this in MongoDB is to use what's called a write concern. And the write concern is the number of nodes in the replica set that have to save that data to disk before MongoDB acknowledges back to the application that that write is complete. So in this simple example here, that W2 means 2 nodes in the replica set have to save the value to disk before the insert of x is 100 will be acknowledged back to the application. And often, people use a keyword called majority, which is just based off the number of nodes in the replica set. So if a replica set has 3 nodes in it, majority is 2. If the replica set has 5 nodes, majority is 3, and 7, 4, so on and so forth. And in that way, when you issue the write concern, it will be tailored to the size of the replica set. And if your replica set depth changes, you don't have to change your code type of thing. And the advantage of write concern majority is that MongoDB will not acknowledge the write back to the application until a majority of the nodes in the replica set have saved that data to disk. So in this case, with write concern majority, we issued the write. It was saved on the primary. It was saved on one of the nodes. And then we'll get the acknowledgement back to the application. And the advantage of write concern majority is that MongoDB guarantees that if a failover occurs in this scenario, the node with the current data, in this case node 3, would become primary. And there wouldn't be any perception of loss of data in a failover because the node that took over as primary will have the write that we just made with write concern majority. So with all of that, I think that should give you an intuitive feel for how you can tune MongoDB along all of these dimensions, right? So how we can tune consistency, availability, durability, and how the impacts are on performance. Essentially, the more durability we add, that's going to mean our writes take longer as we have to wait for them to replicate across to different nodes. So that means our write performance in terms of latency is going to be longer, right? So you can make these trade-offs. And then based upon the requirements of your application, maybe you have an application where you want, the primary goal is to do, 50,000, 100,000, million writes per second. And if occasionally we lose some information because of failover or something like that, we can tune MongoDB to deliver on those requirements. So we can, read from secondaries to scale reads. We can just use a write concern of 1 so we get the highest write performance possible. And that will give us an application that is optimized for performance. And we're going to sacrifice some durability and consistency for doing so. Similarly, we might have let's say it's an online banking application where we never want to show a customer an inconsistent view of the data. We never want to lose any information when we lose regions or data centers or anything like that. And we can tune MongoDB in the exact opposite way so that we're using a really high write concern and we're using things like read concern majority to make sure that the customer is always getting the most consistent view of the information. So that's kind of one, so what we've done thus far is kind of talked about how we can trade off these different parameters in MongoDB. Let's now switch over and talk about how we can lay out replica sets to meet some of the multi-data center or multi-region requirements. So if you're talking about deploying MongoDB across multiple data centers, there's really essentially 3 architectural topologies that you can choose. One is really simple, called ActiveDR, which I'll talk about. The second is to use zone sharding to essentially put primaries in multiple regions so that you can do local reads and writes in each region. And the third is to do kind of a pure MultiMaster type solution with Mongo. So let me kind of talk about those 3 options. All right, so option 1. So in option 1, you're not doing ActiveActive. So you're wondering, why would I talk about this in an ActiveActive presentation? Because often in some organizations, what ActiveActive means is we're going to have a primary data center, we're going to have a DR data center, but the requirement is that failover is almost immediate within a few seconds. If that's your definition of ActiveActive, then MongoDB using a replica set is going to be the ideal solution, because that's the way replica sets work, right? You can put the primary in the region where you're going to be actively processing requests. You can have secondaries distributed across a bunch of other regions. And then if you lose a region or a data center or something like that, the replica set is going to automatically fail over. It's going to do that in 2 seconds as long as you've handled the app server failover process as well in under 2 seconds. This is going to just work. It's not going to require much configuration. You can tune the read concerns and write preferences and all those things to meet your consistency and durability and availability guarantees. But this is just going to be real work, and it's going to be real simple. So if that's your requirements, do this, because anything I talk about next is going to be a lot more complicated, and why do that if the simple thing works? All right, so let's assume that that's not good enough. You need pure ActiveActive. So the next option is to leverage zone sharding and essentially use multiple shards to just put primaries in multiple regions so you can handle writes in multiple regions. So let's talk about how we're going to accomplish that. So the way we're going to accomplish that is we are going to assume that there is this process that's upstream that routes requests to each of my data centers, each of my regions, based upon geography. So in this scenario, hypothetically, I'm a US company, and I've got 2 regions. I've got one in Oregon, I've got one in Virginia, and this request router is going to route all the customers who reside on the western half of the US into the Oregon data center, and it's going to route requests for all customers on the eastern half of the US into the Virginia data center, and it can do that based upon the location of my mobile device or my IP address. It might be done based upon your zip code and your account or whatever, but we're just going to assume that that process exists. And if that exists, then what we can do is we can organize MongoDB in the same way. Leveraging zone sharding, we can create multiple zones, east and west, and then associate replica sets in our sharded cluster with each of those zones. So the replica set for the Oregon, in the Oregon region and in the western zone will have its primary in Oregon, and the replica set for the eastern zone will have its primary in Virginia. And that means that if I am a customer and I get routed to Oregon, because I'm living in California, for example, my requests are going to get routed to that app server on the left, or actually that's your right, and it'll be processed by the local primary in that region. And similarly, if I am a customer in Philadelphia, I'm going to get routed to the app server in Virginia, which will then have a local primary that it can do its writes to in Virginia. Also, with this architecture, if I need to do analytics, where I want to essentially look across all the customers, I have local instances for all the data in each region, so I could do some sort of complex aggregation query and understand my customer set in its entirety as well, because I have data from each of those zones in each region. And keep in mind that there's no requirement in MongoDB that when you set up these zones, you can have multiple shards in each zone. So if I have a lot more customers in the East Coast, I could have 2 shards for my East region and 1 shard for my West region. All right, so how you'd implement that is basically you pick a shard key that's typically something like region code and user ID. And in each document, whether that's an account or a shopping cart or whatever, you assign that region code. So in this case, for this particular customer, they live in Arizona, so their region code is West. And in this case, we're going to shard based upon the region code and this user ID. And then in MongoDB, if you're using Ops Manager or something like that, it actually has a UI where you can build these tables. You can also do it programmatically. But basically, you set up these zones. And in this case, we have 2 zones, West and East. And for the West zone, the range of possible values of the shard key is essentially the region code must be West, and it can be any value of user ID. And similarly for East, the Eastern region, the region code must be East and any value of user ID. And then if you just kind of think about how the collection is broken up into chunks, you'll see that all of the chunks where region code is East will be in the Eastern regions, and similarly for West. That's essentially how you set that up. And you can do this I showed it for 2 regions. We could do it for 3, 4, 5, 6. In this case, we've got a zone sharding implementation where we have 3 zones, 3 replica sets. One zone, the green one, has a primary in New York. The other zone has a primary for European customers in London. And the third zone, the black one, has a primary for Asian customers in Sydney with secondaries in the other regions. So you can use zone sharding to essentially do an ActiveActive implementation. Sometimes you'll get pushback like it's not possible for us to have that routing process. So if you can't have that routing, it's going to be much easier if you can. Sometimes it's not possible to do that routing process. So what's the last option? So the last option is do pure MultiMaster. So how would you possibly implement that in MongoDB since we can only have 1 primary? So let's talk about that. So what we're going to do in order to implement a pure MultiMaster is to change the way we write our application a bit. So we're not going to allow any updates. We're only going to allow inserts. And the reason why we're doing that is that eliminates the conflict resolution problem. It eliminates the eventual possibility that we could update the same record in 2 different regions at the same time. If we're only allowing inserts, then records never change. So like if you're doing some sort of CQRS implementation, event sourcing, this would be perfect because that's what those implementations do as well. And then for reads, we're going to essentially have to, because we're inserting information everywhere, we're going to have to essentially do scatter-gather queries, read across all the shards, and aggregate the data. So let's show how that actually works. So I'm going to walk you through a simple shopping cart application, how you could convert a shopping cart application from an update application to insert only. So this is a really simple shopping cart application. We've got our shopping cart documents out on the right-hand side where we've got the shopping cart ID and the list of items in the shopping cart. And on the left-hand side, we've got the code to find a shopping cart and to update a shopping cart. So pretty simple. If we want to convert this to insert only, what we do is instead of having documents for a shopping cart, what we do is we just keep track of the changes to the shopping cart. So in our shopping cart, instead of having a shopping carts collection, we essentially have a shopping cart operations or shopping cart transactions collection where we keep a history of the changes that were made. So in this case, in our collection here, there were 2 add operations that were made to our shopping cart. One operation is somebody added shoes, and then they added a coat. In the bottom left-hand side, we also have the code where we would essentially be used to add that say, hey, now they want to buy socks. And then if we want to essentially display the shopping cart on the screen, we need to essentially apply all of these changes and build the shopping cart. So in the upper left-hand corner, we have the aggregate query that essentially finds all of the changes that were made to the shopping cart and builds the shopping cart document and returns it back to the end user. Right? So that's kind of an example of how you can take code that was designed for using updates and convert it into insert only. So once we've done that, we can then deploy our MultiMaster application in MongoDB, and essentially what will happen is we will just, whenever we get a change, we're just going to insert it into the local primary in the region. So there's going to be no request router. So requests can be routed to any region at any time, and when that app server gets the request, it's just going to insert the change. It's just going to make the change into its local primary. So if you think about the shopping cart example, my shopping cart will have changes. Some of those changes will be in the Oregon zone, and some of those changes will be in the Virginia zone. And when I want to understand what my shopping cart looks like right now, I'm going to have to do a query across multiple zones. So let's kind of like talk about how we implement that. So what you would do in this scenario is you would have a shard key consisting of the data center and some other value that you would use as a shard key that has high cardinality and randomness and all this stuff. So in this case, we would use the data center and the shopping cart ID, and we would set up a zone sharding table just like before, but in this case, we're using the data center instead of the region that the user belongs to. And then the way the actual code looks like is when we go ahead to insert the shopping cart, this DC field would be assigned by the app server. So if my request is routed to the West Coast region, then I'm going to be hitting an app server in Oregon, so it's going to add the data center field to Oregon, and that's going to ensure that the write is going to go to the local primary. Similarly, if my request gets routed to an app server in Virginia, it's going to set the DC field to Virginia, and that's going to ensure that that write goes to the local primary in that region as well. And then the aggregate query is the same as I showed before. So when you want to do a read, though, you don't know where. The nice thing about the zone sharding that I showed in option 2 was because we knew what region the user belonged to, we knew where that user's data was, and we could send that request to just the nodes associated with that region. In this case, because we're inserting data for each user, each shopping cart in all the regions, when we do a read, we have to do a scatter-gather query and send our reads to all of the nodes, to one node in each shard, so we can pull all the data together and build the current picture of whatever we're trying to build, like a shopping cart. So the cost of this, besides having to convert our workload from update to insert only, is that our reads are going to be more expensive. Because in this case, in order to read a shopping cart, we're going to have to look at multiple documents and do some processing. Plus, we're going to have to query nodes in multiple shards. So this is just another example of how we gave ourselves a lot more write availability, but we're essentially going to pay the little bit of price on the read side. All right, so just to kind of conclude, in terms of the options I went through, we could do an active DR solution, real simple, gives you consistency. The downside for that one is that the writes in remote data centers are going to be slow because they have to go across a great distance. We can use zone sharding, and we can build a pure active-active solution. It'll be consistent. There'll be no conflict resolution. It does require an external routing process. And sometimes that's a showstopper. Sometimes it's easy. It just depends on your particular business situation. And then we could also do a pure MultiMaster type solution. We don't need the external routing process, but we do have to do this conversion from an update process to insert only. And we're going to make some trade-offs there in terms of our writes are going to be really fast, but we're going to pay a little bit of penalty on reads. And keep in mind, all of those architectures can be tuned based upon the consistency, the read and write availability, and durability you need to meet your requirements. So my hope is the next time you have an application and you're looking at MongoDB, this will give you kind of a better framework to determine, hey, is MongoDB a good fit for this, and could we configure it to meet those requirements or not? So with that, I think we have a few minutes for questions. I'll be happy to entertain any questions. So I think Nick's going to bring you the mic.
So one question regarding the MultiMaster.
Yep.
You spoke about the object ID that was generated. Where does that object ID come from? Because if you had multiple app servers and they were generating the ID, is there a possibility that an ID you might have a conflict? I mean, you could use a GUID, but.
So you're talking about like for the shopping cart ID for this scenario here? I mean, so in theory, is it possible that if I went to create a shopping cart, I guess it might be possible, depending upon the use case, for you to possibly create two shopping carts at the same time. I don't know. You might have to engineer that. Yep. All right, looks like we got one more question. And I'll be happy to stay around for any questions as well.
Couldn't have been less convenient placement. Has anybody considered a solution in which there are multiple clusters, one in each region, with inter-cluster replication performed?
So that's not, I mean, I think that's a theoretical solution. It's not an option that MongoDB offers today. I mean, there is a tool called Mongo Mirror where you could potentially build something like that yourself, but I got a feeling there's probably a bunch of edge cases.
Is there a good engineering reason not to do it?
I think the reason why MongoDB is architectured the way is, as a philosophy of the database, we believe that consistency is the most important parameter. Once you start allowing writes in multiple regions and have replication across, you're going to have to deal with conflict resolution. And then you lose writes at that point. But I think there are use cases where that does make sense. Yep. All right. I think we're all done. So
that's it.
Thank everybody for attending, and I'd be happy to stick around and take questions.